Hi there, Mrs. Thompson here, and today we're going to go over drawing Lewis structures for covalent compounds. Okay, before we begin, I just wanted to discuss the simulation that you did. In the simulation, you looked at different atoms with different amounts of valence electrons. So for example, if I looked at fluorine, it has 7 valence electrons. And if I have 2 fluorines together, they each have 7. According to the octet rule, each one want to have 8 valence electrons to complete their shell and to make them a more stable molecule. And so since each one of these only need one more, what they decide to do is they decide to share. And so these 2 electrons will be shared between both of them and form a single bond here. And then it got a little more complicated when you had to form double bonds and triple bonds. So for example, in this oxygen molecule, if we have 2 oxygen atoms with 6 valence electrons, it means that each one of these oxygens has 2 more places that it needs to fill in order to have an octet. And so the easiest way for oxygen to do this would be to share here and here. And you would have a molecule that looks like this. Now, making structures this way with available spots for bonding works for some molecules. It doesn't work for some of the more complicated ones. And so we're going to learn a series of steps instead of kind of checking and guessing in order to figure out the formula. So we're going to follow some sort of logical pattern. Okay. All right, so here we go. Here are our steps to do this. Before we begin, here's the key. You need to know that each dot is representing 1 electron. That's what E minus is. If you have a line between 2 atoms, it's representing 2 electrons, which means that we can have some single bonds with 1 line, and they're sharing 2 electrons, some double bonds with 2 lines, sharing 4 electrons, triple bonds with 3 lines, sharing 6 electrons. Okay, so that's the key to kind of understanding what's going on. All right, so then what are the steps? First step, count the number of valence electrons. I'll show you how to do that. Second step, figure out the central atom. And so it really has to do with electronegativity, but there are a couple of tricks that you can use to figure out the central atom that I'll explain in just a minute. All right. Number 3, draw single bonds to outside atoms. And I'll show you what that looks like. 4, fill the octet for outside atoms. And this is an exception to that. Hydrogen can only handle 2 electrons. Remember that hydrogen looks like this, right? To start out with, hydrogen has 1 electron. It can only form 1 bond with that 1 electron. If we were to look at each hydrogen atom, we'd have 1 proton in the middle, 1 electron. It only has that 1 s electron here. And so it can't accommodate any more electrons. So it's done as soon as you have 2 electrons. All right. Number 5, put the remaining electrons on the central atom. 6, check the central atom for an octet. So remember that's 8 electrons. If it does not have an octet, we're going to try some double bonds or triple bonds, and you'll see those in our examples. Okay. Here we go. So we'll start with the single bond examples. Now the first step was to count the valence electrons. So we're going to do that for each element. We have phosphorus and hydrogen. And what I'm going to do, let me zoom in here. Is for each one of these, I'm going to take the number of atoms and multiply that by the number of valence electrons for each element in my formula. Okay, so according to my formula, I have 1 phosphorus and 3 hydrogens because it's pH3. Now, let's figure out the valence electrons. So I want to remind you that in order to do valence electrons, we look at group numbers. For the group A elements, all you have to do is look at the group number. So if it's under group 1A, has 1 valence electron. If it was under 5A, it would have 5 valence electrons, and so on. So this only works for group A elements. So if we look for phosphorus, here's my periodic table. Phosphorus is under group 5A, so it has 5 valence electrons. And hydrogen is under group 1A, it has 1 valence electron. So it'll be 1 times 5 for phosphorus and 3 times 1 for hydrogen. Okay, so that's 5 and that's 3. We're going to add these together to get a total. All right, so what that means is I'm going to be working with 8 valence electrons in order to make this structure. Okay, that's step 1. Figure out the number of valence electrons. Step 2, determine the central atom. Okay, so I said it's the one with the lowest electronegativity. Remember that the trend works like this. I guess this is a bad way to show it. Let's look at this smaller periodic table. As I go from left to right, the electronegativity increases. And as I go from top to bottom, it decreases. So the overall trend for electronegativity is diagonal. Okay, which means the highest electronegativity would be right here because we don't count the noble gases. They don't really form too many compounds. And the lowest would be over in that bottom left corner. Okay, so then if we're looking at phosphorus versus hydrogen, phosphorus is here, hydrogen's here. There's a good chance that phosphorus has a lower hydrogen has a lower electronegativity than phosphorus. One thing you need to know is that hydrogen can never be a central atom. The reason it can never be a central atom is because it can only form one bond. So if it can only form one bond, it can't branch off and form multiple bonds around it. Okay, so I could also look at my formula. I only have 1 phosphorus and I have 3 hydrogens, so it makes sense that phosphorus should be the middle atom. Even if I wasn't looking at electronegativity, this should make sense. So I'm going to put the phosphorus in the middle. Okay. Next one, draw single bonds to the outside atoms. So I'm going to put my hydrogens around the phosphorus. I have 3 of them according to the formula. 1, 2, 3. Okay, I'm going to draw single bonds. So there are my single bonds. I'm going to keep track of my electrons. So let's do that. I started with 8, and I'm just going to subtract the number of electrons that I've used. Since I have 3 lines and each line represents 2 electrons, I have used 6 in total. This leaves me with 2 electrons. Okay, so I've taken care of steps 1 through 3. Step 4, fill the octet for the outside atoms. Except hydrogen, it only needs 2 electrons. So hydrogen is full. We can't put any dots on hydrogen. So never, ever, never put dots on hydrogen. So where do these 2 dots go? Step 5 says put remaining dots on the central atom. Well, I have 2 left over. I'm going to put those on the phosphorus. So those are my 2 electrons that I have left over. Okay. That leaves me with 0 left over. Okay, we're going to check, it says in step 6 to check the central atom for an octet. We'll worry about the if it doesn't in just a second. Okay, so let's count. Phosphorus has these 2, plus each one of these 2, so 2, 4, 6, 8. Phosphorus has an octet. Okay, it has 8 valence electrons. As soon as that's true, you can call this molecule finished. Okay, it's done. I don't need to do anything else with it. If it wasn't true, we would do the next part of 6. Okay, but because phosphorus has an octet, it's finished. Hydrogen, on the other hand, has what we call a duet. It has 2 electrons, and that's all that hydrogen needs. So octet, 8 electrons on my phosphorus, duet, 2 electrons on my hydrogen. Okay, in case I didn't make that clear earlier, and I don't think I did, this hydrogen and this phosphorus are actually sharing those 2 electrons. So they count for both the hydrogen and the phosphorus. Okay. All right, let's try this one. Okay, so I'm going to go through and count up all of my atoms. So I've got 1 carbon, look for capital letters, 1 hydrogen, and that's a chlorine. So 1 of these, 1 of these, and 3 of these. So looking at the periodic table, remember that the group A elements tell you how many valence electrons. So carbon has 4, hydrogen has 1, and chlorine right here has 7. 7A, 7 valence electrons. Okay, so that's 4, that's 1, that's 21, and so then a total would be 26. So we have 26 valence electrons to work with. All right, let's move on to the next part. Determine the central atom. Okay, so let's ignore the whole electronegativity thing and let's look at the formula that we have. I've got 1 carbon, 1 hydrogen, and 3 chlorines. Chlorine can't be my central atom because I have 3 of them. We want something else to be the central atom. It's either going to be carbon or hydrogen. Can't be hydrogen, so it must be the carbon. Okay, so what I'm going to do is I'm going to put 1 carbon in the middle, and then put the chlorines on the outside. It doesn't matter, honestly, where you put them. I also have my hydrogen. So I could have put the chlorine here and a hydrogen here. I could have switched this up as long as I've got 3 chlorines and 1 hydrogen. Okay, so that was count the valence electrons, determine the central atom. Step 3, draw my single bonds. Okay, now you have to keep track of the math. And the reason for this is because half the time when I go to check students' work, I can find their mistakes because they've subtracted wrong. And so I can't tell how to help you unless I can see your subtraction. Okay. All right. So there we go. 26. So we're starting out with 26 and I've used some. Each line is worth 2. I have 4 lines, so I've used a total of 8 electrons out of the 26 that I have available. If I subtract 8, I get 18. Okay, next step. Fill the octet for the outside atoms except for hydrogen. So I don't do anything to hydrogen, but these chlorines can take more electrons. Right now, each one of those chlorines only has 2, so it needs 6 more. So if I put 6 here, that's its octet is filled. 6 here, Okay, so now I've used 6 plus 6 more, that's 12. Plus another 3 is going or sorry, 6 is going to give me 18. So I've just used all 18 of those, leaving me with none left over for the central atom. So if you get a 0, that means the central atom doesn't have any to put on there. No extra dots on there. Again, notice I didn't put any dots on hydrogen. It is done as soon as it has a bond. All right, next part. Check the central atom for an octet. Okay, so carbon has 2 here, 2 here, so 2, 4 altogether, 4 bonds, so that's a total of 8. So carbon does have an octet. And I'm just going to write octet check mark. I've checked that step. Good. Okay. Here's another example. We've got Br2. This is one of my diatomic elements. It's bromine. There isn't anything harder to this one than the previous ones. It's just sometimes I have students not sure about what to do just because there is an essential atom on this. It's just 2 atoms. So if I have bromine, we have 2 atoms of bromine, and then I got to look up bromine. So bromine is right here under 7A. So that's 7 valence electrons for 14 in total. Okay. We'll put bromine next to each other. No real central atom. So bromine, bromine. I'll draw my single bond to the outside atom. So let's say that's the central, that's the outside. Really, it doesn't matter. Okay, we'll do the math for that. So 14 minus 1 bond, which is 2, leaves me with 12. All right, I know each of these bromines needs an octet, so each of them are going to need 6 more. So there's my 6 dots on this one, 6 dots on that one, and now I've got a total of 12, so none left over. Okay, notice I'm taking my subtraction all the way to the 0. All right, next part. Hopefully you're doing all right. All right. So the next part of this is drawing examples or drawing molecules for polyatomic ions. Remember that polyatomic ions are covalently bonded, so we can draw their Lewis structure for a covalent bond here. Some of our polys are negative. The way that they become negative is that they have gained electrons. And so what we're going to do is we're going to add electrons. We're going to add their charge. So that'll tell us how many they've gained. Sometimes they're positive. That means they've lost electrons. And so we're going to subtract the number equal to the charge. And then we just have to redraw this with brackets and charge. I'll draw a line in between these to separate them out a little better. Do that. This one too. Okay, so first step, we'll just worry about the phosphorus and the oxygen. I have 1 phosphorus in the formula, 4 oxygens in the formula. Phosphorus is right here in group 5A. It has 5 valence electrons. Oxygen is in 6A. So this will be 1 times 5, and this is 4 times 6. Okay, the other thing that we have is we have a -3 charge. Again, this means that it has gained electrons. It's gained 3 of them. That's why it's a -3 charge. Okay, so that means we're going to add 3. So if I add this up, I get 32 2 electrons that I'm going to work with. You'll notice it won't make much sense if you try to do it the other way. You'll end up with strange structure. So negative means gained electrons. You add those electrons to the charge. Okay, so then we'll put, of these 2 atoms, phosphorus, I have less of them, so that's going to be my central. We'll put oxygen on the outside. Okay, I'll draw single bonds to the outside atoms. And then I'll subtract. So it's 32 minus the 8 that I've just done. So that is 24. Okay. Each one of these oxygens can hold 6. I have 4 of them. 6 times 4 is 24. So looks like each one gets 6. Make sure you figure that out before you start doing this. And you probably want to do these in pencil. So that way, if you make a mistake, you can erase and not have to start over. Okay, so I have 0 left over to put on the central atom. I'm going to check this for an octet. I think I forgot last time. So each one of my oxygens have an octet. So does the phosphorus. It's got 2, 4, 6, 8. So I'm just going to write on the bottom. We'll do that. Octet. Check. It's got an octet. All right, I'm almost done. I have to complete this structure with brackets and a charge. So here's what I mean by that. This is PO4 in a bracket. All of that goes inside. The charge goes on the outside, 3 minus. This is often left off, so don't do that. Make sure you get all of it. Don't lose that point for the charge. Okay, we'll try this one. All right, now I have hydrogen. There's 3 of them in the formula. Each one is in group 1, so that's a 1 valence electron. Oxygen, I have 1 of them in the formula. Each oxygen has 6 valence electrons. Okay, and then I have a plus here. That means it has lost 1 electron. So I'm going to subtract, not add. So whatever this sign is, right? You're basically doing the opposite. I'm going to subtract 1. So that would be 6 plus 3 is 9, minus 1 is 8. Okay. Figure out the central atom. It can only be oxygen. Hydrogen, it can't be a central atom at all. So I'll put the oxygen in the middle, the hydrogen's on the outside. We'll draw single bonds to the outside atoms. Okay, we'll do the math. 8 minus 2, 4, 6 is 2 valence electrons. Okay, I have 2 left over. They can't go on the hydrogen. Do not be tempted to put dots on hydrogen. As soon as you have a single bond to hydrogen, it is finished. Okay, so where do we put those? We put those on the central. Right here, 1, 2. Another thing, when you do this, when you're putting your electrons on the central, you keep them in pairs. They like to hang out in pairs. Just like when I put the dots around the chlorines here, you keep them in pairs. Don't split them up. All right, this is almost done. We're just missing brackets because normally if this was just regular old hydrogen with oxygen, like in this ratio, it wouldn't have a charge, right? So wouldn't have this many electrons. It would have 1 more electron. So to say that it's missing an electron, we put that +1. Okay, we're almost done. Sometimes it's not enough to have just single bonds. We have multiple bonds. So it says double and triple bonds become necessary when the central atom does not have an octet. They also go on to say never force double and triple bonds to exceed an octet. Once you get your octet, I'd like you to finish. Just stop, 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 stop. Okay. All right, so here we go. Same steps. We have carbon and oxygen. I'll zoom in. We've got CO2, carbon dioxide. Okay. One of them, each carbon has 4. Oxygen, there's 2 of them. Each oxygen has 6 valence electrons. Make sure you look those up. Okay. Add them up. All right. Between carbon and oxygen, a couple things. Carbon has a lower electronegativity than oxygen. You just look here, it's further to the left. Oxygen is more electronegative than carbon. Also, there's only one carbon in the formula, so it makes sense for it to be the central atom. So I'll put one carbon here, oxygen here, oxygen here. I'm gonna run out of room. Let's make this example long. This will be the last thing we do. Okay, so I'm gonna draw single bonds to my outside atoms and subtract. So now I've used 2, 4 electrons. So that leaves me with 12. Okay, each of these oxygens can hold 6 more. So let's go ahead and do that. If I have 6 on this one and 6 on this one, then each oxygen has an octet. So minus 12 is 0. Problem though, my carbon doesn't have an octet. And because my carbon doesn't have an octet, I am not finished with this problem. Okay, what I'm going to have to do is force some double bonds and some triple bonds or whatever it takes to make it have an octet. Right now, carbon only has 2, 4. Okay, so what I'm going to do is I'm going to move some electrons around. I'm going to force this oxygen, since it has an octet already, to share some of what it has with the carbon. So if I do that, and I turn these 2 dots into a bond here, that's going to look like this. Okay, then I'm going to reevaluate it and see if I've got octets yet. This oxygen still has an octet. It's got 4 here plus these 4. This oxygen still has an octet. It's got 6 here plus these 2, so that's 8. But my carbon still does not have an octet. Okay, it's only got 2, 4, 6. Better than here, but not done yet. All right, so what you're going to do is you're going to go ahead and steal from the other side. That's what we say. So you steal from this side already. Let's go ahead and steal from that side. So these 2 are now going to form a double bond. So what it'll look like is this. Okay, and be very careful with those extra dots that you draw. Right? If these were here before, they need to be here afterwards. All right, so on paper, if you do this version, what I want you to do is box your final answer. Remember, you're checking to see that each one has an octet. Box your final answer. If I were doing this on paper, I wouldn't do it that way. I'd just use my ability to erase because I have a pencil. right? So I would start out here and just go, okay, well, this needs to form another line. So there's a double bond there, but it's not done yet. So we need to erase these two and move on. As long as you have a good eraser, you don't need to show these in between steps. If you don't, and you have to show multiple, then I want to see which one is the final answer. Okay. Last example. We've got carbon and oxygen again, but this time we have carbon monoxide. Ten valence electrons to work with. Carbon, oxygen, one line in between. That's 2 electrons, leaving me with 8, which means I have how many? I could put 4 on this one and 4 on that one. Let's do that with pencil. 1, 2, 3, 4. 1, 2, 3, 4. Okay, now I've used all 8. None left over. And once you reach 0, you can stop. You don't have to redo your math at all if you have to share more electrons than you did before. Okay. All right, so here we go. Let's go back to this. We don't have octets on either, so we're going to have to start erasing and making them into double bonds. So we'll start with this one. So that becomes a bond. And now the carbon has 4 here and 4 here, so it has 8, but the oxygen only has 4 plus 2, which is 6. So we're going to have to do that again. We'll erase these 2 this time. So share from the other side. And now what we see is we have a triple bond between the carbon and the oxygen. And it's got 6 that they're sharing, and then they each have 2 on their own. So that's why they both have 8. All right. Questions I normally get. This could also be written with the dots on the top. So sometimes people have this instead. It's the same thing. Okay. All right.